What if the next food revolution did not begin in a field but in the silent, sunlit vacuum of space? Imagine walking into your local supermarket and seeing two options side by side. One is a familiar package of ground beef, its price shaped by seasons, soil, and supply chains, stretching across continents. The other is a sleek container of protein powder, its label proudly stating "Made in Orbit." The most astonishing part is not its origin, but its price tag, which is noticeably lower than that of the beef. This simple economic shift could trigger a cascade of changes, reshaping not just what we eat, but the very fabric of our global food system. It is a future that prompts us to look up at the stars and wonder about the fields below. This scenario is no longer confined to the realm of speculative fiction. It is a tangible possibility being explored by scientists and entrepreneurs today. The core idea is that producing protein in the controlled environment of a space station could, one day, overcome the immense costs of traditional agriculture. We are not talking about a distant, far-fetched dream, but a potential reality hinged on technological progress and economic tipping points. So, what exactly is this space-grown protein that could one day fill our shopping carts? In simple terms, it refers to edible protein cultivated in a low-gravity environment, far above the Earth's surface. This is not one single product, but a category that encompasses several innovative methods. Visual, plant-based path. Visual, cell-based path. The first and most straightforward approach involves growing plants. Specialized orbital greenhouses could cultivate high-protein crops like soybeans, quinoa, lentils. Using advanced hydroponics or aeroponics, these plants could be grown with recycled water and nutrients under constant optimized LED lighting, potentially yielding harvests far more rapidly and reliably than their terrestrial counterparts, which are subject to weather and pests. A second, more technologically advanced method involves cellular agriculture. Visual vial of cells plus nutrient. Visual bioreactor. Visual harvested protein mass. A small sample of cells from a cow, chicken, fish is placed in a bioreactor, a sterile temperature-controlled tank. Inside, these cells are fed a nutrient-rich liquid medium, sugars, amino acids, minerals, which provides them with the building blocks to multiply and grow. This process, happening in the unique conditions of microgravity, could potentially produce pure muscle tissue, which can then be harvested and processed into a protein-rich food product, sidestepping the need for a living, breathing animal entirely. The third major pathway involves single-cell organisms, such as yeast bacteria. These microbes are nature's protein factories, capable of converting simple inputs into complex proteins with incredible speed and efficiency. In an orbital bioreactor, a culture of specialized microbes could be fed a simple feedstock, perhaps even processed waste, from the space station itself, turning it into a high-quality protein powder. This method holds a powerful incentive: its potential for extreme resource efficiency. The feedback loop here is compelling. The more protein is produced, the more potential waste is available to be recycled back into the system, creating a nearly closed-loop production cycle that is difficult to achieve on Earth. Regardless of the method, the system of producers is a new and specialized network. Aerospace engineers, biologists, food science companies, investors, regulatory agencies. Each part of this chain, from the rocket launch to the dinner plate, introduces its own costs, delays, and potential bottlenecks that must be overcome. To appreciate why space protein could become cheaper than beef, we must first understand the journey from a concept to a consumable. The entire process can be broken down into four fundamental stages. 1. Transportation. All the necessary raw materials must be sent from Earth into orbit: seeds or cell cultures, nutrient medium, and the very hardware of the factory itself. Today the primary constraint is launch cost, measured in thousands of dollars per kilogram. A significant reduction in this cost, perhaps through reusable rocket technology, is the critical threshold. Once the materials arrive at the orbital factory, cultivation begins. In a plant-based system, robotic arms place seeds into growth trays under precisely calibrated light and nutrient flows. In a cell-based system, the process is more like a brewery. Technicians or automated systems introduce the cell culture into a large bioreactor filled with growth medium. For weeks, the system is carefully monitored. Temperature, oxygen levels, sterility. That delay still represents a production timeline to factor into the economic model. Any contamination or equipment failure during this stage could mean losing an entire batch. The third step is harvesting and primary processing. For plants, this might involve automated trimming and threshing. For cellular protein, the dense mass of cells is separated from the liquid medium. It is then rinsed and dried to create a stable, concentrated protein powder or paste. This initial processing in space significantly reduces the mass that needs to be sent back to Earth. It's far cheaper to transport a lightweight powder than a heavy water-filled product. The fourth and final stage is the return trip and distribution. The processed protein is packaged into specialized re-entry capsules designed to withstand descent. After landing, these capsules are collected. Their valuable cargo is transported to terrestrial food processing facilities. Here, the space protein is mixed with other ingredients and flavored, shaped into familiar forms: burgers, sausages, nutritional bars. Then it moves through the conventional food supply chain, factories to distribution centers to grocery store shelves. The entire logistics chain, from launch to landing, is a complex system with many potential delays and failure points that must be flawlessly managed. The first ripples. Immediate consequences for our plates and pockets. If space protein crosses the price threshold and becomes cheaper than conventional meat, grocery stores and kitchens will feel it first. Supermarket chains would be among the first adopters, driven by the incentive to offer lower prices and attract customers. New product lines would appear on shelves, labeled with their novel origins. Initial offerings likely in processed foods, frozen burger patties, pre-made pasta sauces, protein bars, where texture and form matter less. Lower prices attract budget-conscious shoppers, increasing sales and pushing retailers to stock more. That shift sends a shockwave through the agricultural supply chain. Demand for some meats, especially ground beef used in processed products, would drop. Downward pressure would hit the prices farmers receive for livestock. Ranchers and cattle-dependent farmers could see swift, significant income drops. The effect would ripple outward. Demand for animal feed like corn and soy would soften too. The whole system, tuned over decades, would be forced to react. The disruption won't be uniform globally. Major beef-exporting regions would feel it most acutely. Economies reliant on agricultural exports could face trade imbalances. Conversely, nations with aerospace and biotech industries might boom, creating new exports. That creates a delay. Negative impacts on farming could be immediate, while the positive gains from a new space industry would take years to build. Restaurants and large-scale food services, fast food chains, hospital cafeterias would be key players. For them, ingredient costs drive profitability. The incentive to switch to cheaper protein would be huge, especially one with stable price and supply not subject to droughts or disease. A fast food chain could reformulate its signature burger with space protein, lowering costs across thousands of locations. Widespread commercial adoption would normalize the ingredient for millions and accelerate acceptance into mainstream food culture. Shaking the system, widespread impacts on planet and people. Beyond the immediate economic tremors, the rise of affordable space protein would trigger profound system-wide impacts that unfold over years and even decades. One of the most significant areas of change would be the environment. Traditional livestock farming is a major contributor to greenhouse gas emissions, particularly methane, and is a leading driver of deforestation as forests are cleared for pasture land. A substantial reduction in the global cattle herd could lead to a corresponding decrease in these environmental pressures. This presents a positive feedback loop. Less demand for meat leads to less deforestation, which in turn helps mitigate climate change, potentially improving conditions for all forms of agriculture. However, the environmental equation is not entirely one-sided. The models diverge on the net impact when the energy costs of space production are fully considered. Building orbital factories, launching orbital factories, operating orbital factories. While these facilities would likely be powered by massive solar arrays, the manufacturing of those panels and the rockets themselves carries a significant carbon footprint. The critical question, and a point of uncertainty, is the threshold at which the total energy and resource cost per kilogram of space protein becomes lower than that of traditional meat. A comprehensive life cycle analysis comparing the two systems from start to finish would be essential to determine the true environmental benefit. The economic landscape would also be fundamentally reshaped. While traditional farming communities might face decline, a vast new industry centered on space logistics and biotechnology would emerge. This would create new jobs for aerospace engineers, material scientists, roboticists, and biochemists. Entire cities could spring up around launch sites, becoming hubs for this new agri-space sector. However, there is a significant delay and a skills mismatch between the jobs lost in rural farming and the jobs created in these high-tech hubs. Without proactive government intervention, such as large-scale retraining programs and social safety nets, this transition could exacerbate economic inequality between rural and urban regions. Regulatory systems would be forced to evolve at an unprecedented pace. Food safety agencies would need to develop entirely new protocols for testing and certifying products grown in a non-terrestrial environment. Questions about long-term health effects, potential allergens, and the unique properties of proteins grown in microgravity would require rigorous scientific study. The speed of regulatory approval would act as a major constraint or accelerator for the market. A new equilibrium, the long-term food landscape. If we look further into the future, past the initial disruption, what would a world with cheap and abundant space protein look like? Our global food system wouldn't be replaced. It would integrate a major new component, finding a new and different balance. Agriculture would still be essential, but its focus might shift. With less pressure to produce vast quantities of animal feed, more farmland could be dedicated to growing a greater diversity of crops for direct human consumption. Fruits, vegetables, grains. This could enhance food security and improve nutrition for millions of people. In this new equilibrium, the role of livestock farming would also be transformed. It would likely become a smaller, more specialized industry. Instead of mass-producing inexpensive ground beef, farming might focus on high-quality premium meat products, tradition, flavor, provenance. Some farmers might transition to carbon farming or rewilding projects funded by new environmental markets. This represents a systemic adaptation, where a traditional industry finds a new, sustainable niche in response to a powerful market shift, though the transition period would be a significant challenge for those involved. The logistics of our food supply would be fundamentally different. We would have two parallel systems, a terrestrial one, moving food across land and sea, and a new celestial one, managing the flow of resources to orbit and finished products back to Earth. This creates redundancy and resilience. A major drought or disease on Earth might not affect the steady output from the orbital factories, providing a stable buffer against food shortages. The primary constraint in this future state would shift from land availability to energy availability and the long-term durability of space-based hardware, creating new engineering and economic challenges to solve. Ultimately, consumer choice would be far broader. A typical family might eat a variety of proteins throughout the week. They might have space protein tacos on Tuesday for a quick, affordable meal, enjoy a locally grown chicken salad on Thursday, and savor a premium, pasture-raised steak as a special treat on Saturday. This future is not a sterile, monolithic world fed by powder from the sky, but a more diverse, complex, and potentially more resilient food ecosystem. The feedback loop between consumer demand, technological capability, and agricultural practice would have found a new, dynamic stability, forever altered by our decision to look to the heavens for our sustenance. An unwritten menu. The choices we still must make. We have journeyed from a simple question about a price tag to a vision of a profoundly altered world. The possibility of space-grown protein becoming cheaper than beef is not merely a technological curiosity. It is a scenario that forces us to confront fundamental questions about our relationship with food technology and our planet. The system we have explored is one of intricate connections, where a change in a launch cost could eventually lead to the reforestation of a distant continent. We have seen the constraints, like energy regulation, and the powerful incentives, like profit sustainability, that will steer this future. The delays and feedback loops inherent in this global system ensure that any such transformation would be a slow, complex, and often unpredictable process. The models we use to forecast this future diverge at critical junctures. The exact threshold at which space protein becomes economically viable remains a point of intense debate. The true environmental calculus, weighing terrestrial impacts against the energy cost of space industry, is still being written, and perhaps most importantly, the speed and nature of human cultural adaptation, our willingness to embrace such a fundamental change in something as personal as food, is the greatest uncertainty of all. These are not failures of imagination, but honest acknowledgments that the future is not a single, predetermined path but a vast landscape of possibilities shaped by the choices we make today. The journey to this potential future would create both winners and losers. New industries would rise, while old ones would be forced to adapt or decline. This transition highlights a critical tension that technology alone cannot resolve. The distribution of benefits and burdens is a matter of policy planning, collective will. How we choose to support communities affected by this change, how we regulate the new industries that emerge, and how we ensure that the benefits are shared equitably will determine whether this technological leap forward is a step forward for humanity as a whole. The technology may provide a new ingredient, but society must write the recipe for its use. And so, we are left with a final open question that extends beyond economics and engineering. If we gain the ability to produce unlimited, affordable protein in the sterile environment of space, what do we value most in our food? Is it simply sustenance and cost, or is it also tradition, taste, and our connection to the Earth? The arrival of cheaper space protein would not be the end of the story, but the beginning of a new chapter in our human journey, forcing a global conversation about what we want our food systems to be. Now, we turn the question to you. If both were on the menu tomorrow, which would you choose, and why? What scenario should we explore next? Share your ideas below. You've been watching Ifverse, where imagination meets possibility. See you in our next reality.